In this lecture, we'll see how to do classification with logistic regression, and we'll introduce the important sigmoid function. Classification can be used for many kinds of text tasks, like determining positive or negative sentiment, or determining if a message is spam or not spam, or determining authorship. Recall the famous case of the Federalist Papers written by Hamilton or by Madison. And again, remember that for text classification, we have a document X, we have a fixed set of classes, capital C, and then we're going to output a predicted class, Y hat, which is one of these classes in C, given X. And given a sequence of input-output pairs, so remember that we're using the superscripts for each observation, X, and its label Y. For each such observation, we're going to represent it by a set of feature vectors, x1 through xn, and then we're going to give it a predicted class, Y hat, from the set 0 or 1, so binary classification. In logistic regression, we're going to make use of features. Each feature x sub I is a feature expressing some fact about the text, and it's going to have a weight, w sub I, that tells us how important x sub I is to that classification decision. So imagine that one feature, x sub I, might be the review contains the word awesome. And let's say the weight w sub I is plus 10, suggesting that for a sentiment classifier, having the word awesome is a highly weighted positive cue toward the review being positive sentiment. By contrast, abysmal might have a weight w sub j. The feature review contains abysmal might have a feature w sub j of negative 10, which it means that abysmal is highly weighted, but a negative weight, so that's highly weighted toward the negative class. And a different feature, x sub k, the review contains the word mediocre, might be slightly negative. So our weight is slightly negative, leaning us very slightly toward the negative class. So in summary, for logistic regression, we're going to take an input observation. We're going to represent it as a set of features. X will be represented as a set of n features. We'll have a set of n weights, w1 through wn. And sometimes you'll see these weights called thetas, theta 1 through theta n. And sometimes we call the entire set of parameters theta. And we're going to output a predicted class y hat from the set 0, 1. That's binary logistic regression. We'll see later a generalization to multinomial logistic regression where the output could be from some larger set of possible classes, but we'll stick to binary for now. How do we do this classification? Again, the weight W tells us the importance of the feature. We'll also have a bias term, sometimes called the intercept, and that's another real number that's added to the weighted inputs. And we'll sum up all these weighted features and the bias. So we'll just take each feature X and its weight W, and we'll multiply them together, sum them all up, add the bias, and we'll compute a score for the sum of all of these features. In these lectures, we'll represent such sums using the dot product notation from linear algebra. So the dot product of two vectors A and B, written as A dot B, is the sum of the products of the corresponding elements. So here, the sum of all these W sub I, X sub I's will represent as W dot X. So we're going to compute this sum Z, W dot X plus B, and if it's high, we'll say, yep, this is a positive class. This is positive sentiment, let's say. And if Wx plus B is low, if Z is low, then we'll say that it's the negative class, Y equals 0. Our goal, however, is a probabilistic classifier. We'd like to formalize this idea of if the sum is high that I mentioned on the previous slide. We'd like a principal classifier giving us a probability just like naive Bayes did. So we want a model that can give us actually a probability, the probability that Y is 1 given X parameterized by all the weights theta, or the probability that Y is 0 given input example X and again parameterized by theta. And the problem is that Z, Wx plus B, it's not a probability, it's just some number. In fact, nothing forces Wx plus B to lie between 0 and 1. Weights are real valued. It might even be negative. Z, in fact, ranges from negative infinity to positive infinity. So instead, we're going to use a function of Z that goes from 0 to 1. And the function we're going to use is the very useful sigmoid or logistic function. So Y equals sigma of Z. And the sigmoid is 1 over 1 plus e to the minus z, or as we're going to refer to it from now on, 1 over 1 plus x of minus z. Here's a picture of the sigmoid function, so-called because it looks like an S. The function takes a real value and maps it neatly into the range 0, 1. You notice that it's nearly linear around 0, but outlier values get squashed towards 0 or 1. So it's a very useful function. So here's how logistic regression is going to work. We'll compute, we have our features and our weights and our bias term. We'll compute w dot x plus b. We'll pass it through the sigmoid function, and then we'll just treat it like a probability. So now we just have to figure out how do we turn sigmoid outputs into probabilities. Well, we're almost there. So if we apply the sigmoid to the sum of the weighted features, we get a number between 0 and 1. So this will be between 0 and 1. And to make it a probability, we just need to make sure that the two cases, p of y equals 1 and p of y equals 0, sum to 1. And we can do that as follows. We'll just make p of y equals 0 be 1 minus sigma of wx plus b, which is p of y equals 1. So we're guaranteed these two will sum to 1. We can do a little arithmetic here, plugging in 1 over 1 plus x of minus z. By the way, the sigmoid function has a useful property that 1 minus sigma of x is the same as sigma of minus of x. So the probability of p of y equals 0, which we refer to as 1 minus sigma of wx plus b, we could also refer to as sigma of minus wx plus b. We'll sometimes see it in that form. So now, to turn the probability into classifier, our estimate, y hat, our estimate of the class of our example x, is 1 if p of y equals 1 is greater than 0.5 and 0 otherwise. So 0.5 here is the decision boundary. So here I've graphed wx plus b along the x-axis and the probability produced by our sigmoid, y equals 1, on the y-axis. So here's our sigma of wx plus b graph. And here's our decision boundary. So anything greater than 0.5, if wx plus b is greater than 0.5, then p of y equals 1 is greater than 0.5. And we're going to label this example positive. So in other words, given an example x, we're going to give y hat its class 1 if wx plus b is greater than 0, and we're going to call it class 0 if wx plus b is less than or equal to 0. We've now seen how logistic regression uses the sigmoid function to take weighted features from an input example x and assign it to a class y, 1 or 0.